Hello and welcome back. Last time we saw a brief introduction to the JK flip-flop, and this time we're going to actually build the JK flip-flop using the tool called logic.ly. And let's start. So first we're going to start with the outputs Q and Q naught as usual. And then we'll have our inputs. First input is called J, second input is called K. And like the last time we talked about it, we're introducing a new input called clock. And as you can see here, it returns zeros and ones periodically. Now, let's build internal wiring. So let's start with the NAND gate and build the first layer of the feedback. And as we've seen before, the output becomes the other one's input. And then now we're going to have two new NAND gates, which we didn't have in the SR flip-flop. And this is going to integrate the inputs, the clock, J, and the clock with K. And this is going to be our input here. And some of you might notice that this isn't exactly what we've seen in the previous video. In the previous video, these two AND gates had three inputs instead of two. And the reason why I'm doing two inputs right now is because without a properly working previous output, there's no way the second layer of feedback would work and the circuit would never actually run. So we're gonna have a set a previous output by setting J to true, to 1, and now we have a working output. Now let's make the second layer of the feedback. Okay, so the state right now is J equals to 1, K equals 0, Q equals 1, and Q naught equals 0. So now, let's see what happens when I switch J to 0. Before I do that, let's go over it. So let's start with our inputs. This is going to be 0, and let's assume that clock is 1 because only when it's 1 it's actually working. Like only when the clock returns 1, the inputs are going to affect the output. So these two are zeros. Our previous inputs are previous outputs are Q equals to 1 and Q naught is 0, and these gets fed back right here and right here. And now after this, we can see that the first NAND gate on the top will return 1 because two of its inputs are zeros. And the NAND gate at the bottom will also return 1 because one of its input is 0. And because of Q naught being 0 in the previous output, this is going to be 0. And it's going to output 1 because there's a 0 in the NAND gate input. And in the one on the bottom, there's a 1 right here, and therefore the output is 0. And let's see if the circuit has stabilized, because the last time we talked about sequential circuits, we need to analyze the circuit until it stabilizes to produce a truth table. And since our previous outputs didn't change, none of our previous calculated inputs would change. Therefore, the circuit has stabilized. Sorry about that. And because of this, we would assume, if our predictions are correct, when I flip J to be 0, the output Q is going to be 1 and Q naught is going to be 0. And let's see if that's true. Looks like we're right. The outputs Q is 1 and Q naught is 0 when both J and K are switched to 0. Now, let's think about what would happen if we switch K to 1. once again, let's write it out. We're gonna set k to 1 and j to 0, right? And according to our previous outputs, q is 1, q naught is 0, which means that this input right here is going to be 1, and this input right here is going to be 0, which means that we're going to assume our clocks be 1 like we did before, which means that the first NAND gate is going to output a 1, and the second NAND gate is going to output a 0. Once that happens, this NAND gate, the one on the right side, is going to know that it should return a 1. So this becomes a 1, and therefore this becomes a 1. And once that happens, it knows that this should return 0. But before we stop right here, we need to ask ourselves, has this circuit stabilized? And the truth is, it hasn't, because the previous inputs changed. So let's keep going. If if q becomes 0, this will become 0, and this input will become 1. And what about the top? This, because q naught is 1, this is going to be 1, and this is going to be 1 still. And let's see, if this is going to be 1 still, and let's look at q. Q right here is 0, therefore this is 1 remains. And what about the top? If this is a 1, it's a 1 here, 0 remains, and now our circuit has stabilized. Something you might notice is that some of the internal states changed. For example, inputs here, but it didn't really change our output. Therefore, after this run, we know that our circuit has stabilized, and we will predict that when we switch k to 1, q naught will turn to 1 and q will stay at 0. And let's see if that's true. Now I'm going to switch k to 1, and as we can see right here, q naught is set to 1 and q is set to 0, which would mean that our predictions were correct. And now, just for the sake of covering all cases, let's switch k back to 0 and back to the case where both inputs are 0. And before I show you anything, we're going to do a quick run through again. So j is 0, k is 0, our previous inputs. Q is 0, q naught is 1, which means this is a 1, this is a 0, and our clock is 1 every time. Okay, so this would return a 1, and this would return a 1. According to our previous outputs, this will be 0, which means that it still returns a 1 right here. And since it returns a 1 right here, this is a 1 right here, and it returns a 0 right here. And since our outputs haven't changed, we know that our circuit has stabilized, and we would predict if I switch k to 0, the q bit is going to remain at 0, and the q naught is going to remain at 1. And let's see if that's true. And as I've switched k to 0, we know that our predictions were correct. Now let's finish the loop. What if I switch j back to 1? Let me clear the canvas, and let's go through everything again. So q right now is 0, q naught is 1. J will set it to 1, k is 0, our clocks are 1. And this input, because of our previous outputs, this will be a 1 and this would be a 0. This would mean that this output is a 1. The top output will be a 0. Once it sees that 0, it knows that this returns a 1. As it returns a 1, it gets fed back down here, and this becomes 0. And since there's a change in our previous output, the inputs are going to change. Therefore, our circuit hasn't stabilized, therefore we must go on, which means that let's continue. This will be set to 0 because Q naught became 0, and this became 1 because Q became 1. What this means that is that this is going to remain as 1 because K is 0, and the output at the top is going to become a 1 because there's a 0 input now. Once this happens, from our previous outputs, we know that this is a 0, therefore the output remains at 1, and this input is 1 because Q was set to 1, and therefore we know that our circuit is stabilized because our outputs did not change after this iteration, therefore the inputs in the next iteration wouldn't change. And therefore, our prediction would be if we switch J back to 1, the Q bit is going to be set to 1, and the Q naught bit is going to be set to 0. And let's see if that's really going to happen. If I do that, we can see that the Q bit is set to 1, and the Q naught bit is set to 0, just as we predicted. Now we've seen 3 cases already where J is 1, K is 0, K is 0, K is 1, J is 0, and when both inputs are 0. And you probably noticed that this is very similar to the SR flip-flop, where J has almost the exact same functionality as the S bit, the set input, and the K input has almost the exact same functionality as the reset. In the next video, we're going to look at a slightly more complex case, which used to be the error case in the SR flip-flop and a valid state in the JK flip-flop. Let me know if you have any questions, and I'll see you next time.